Come on, computer. And oh, I should probably screencast. Okay. Screencast a lecture, not my music. And here we go. All right, hello. Welcome back, everyone, to another exciting lecture of Data 8. Today, we're going to be talking about transfer regression. Some announcements. So homework 4 is due to make sure you submit it by tomorrow at midnight. Homework 7. Oops. Oh, I wrote 4. Be too sad to see you guys go. It's homework 7, due tomorrow at midnight. Make sure you have that in. We have a guest lecturer coming in on Wednesday to talk about classification. His name is John De Niro. He is the lecturer for the Intro to CS class here at Berkeley, which is a class that has now grown to, I think, 600 students, which is a lot of students. And he teaches Data 8 as well. So he'll be here on Wednesday talking about classification. All right, I think that's it. So last time we ended the lecture, we were talking about a model that we had for regression, right? So linear regression, we have a cloud of points, like we plot some points on the y-axis, points on the x-axis, and we look at those points and we say, okay, it looks like those points kind of fall in like a linearly shaped cloud of points. I'm going to draw a line through that. And what we're doing implicitly when we say there is a linear relationship between x and y, is that we're assuming that there's actually a real line, right? So we're saying, okay, there are points, and even though the points are not perfectly on a line, we think that they are falling on x and y is corresponding to a linear relationship between two variables. We think that there's falling on a linear relationship, and we say, okay, even though they're not perfectly on the line, we think that there is a linear relationship, and they fall off the line because of random noise or like variation in sampling and all of that stuff. So a model is that there is a real line between x and y. Maybe if you gain 10 pounds, your baby will also gain 10 pounds, or something like that, right? So there is a real relationship between x and y. And the points don't fall on the line, but we say that they kind of fall according to this thing here, which says normal distribution with mean 0, which basically means we expect half the points to fall above the real line and about half the points to fall below the real line. Okay, so we have a real line, some points above, some points below. But the important thing here is that we think that there is actually a real line going through your data. That's why we can actually draw that regression line and make predictions. If we thought instead that this was a curve, then we wouldn't draw a line. We wouldn't use linear regression to make a judgment call or prediction based on our data. But because we think that there is a line, we can use a line. We can use a linear regression. Okay. Now, oftentimes in the real world, things are not perfectly linear. You get some when you have a lot of factors coming together to affect two variables, you get some interesting relationships between the two. But oftentimes, a linear relationship, even though it's really simple, is enough to describe formations for a lot of different relationships. Maybe perhaps if you zoom out, there's in fact a really wide curve going through your data. Oftentimes, a linear relationship is good enough. And sometimes, a lot of times in data science, my mic just turned off, huh? A lot of times in data science, we kind of just have to make that judgment call of saying, okay, it looks like our data look like a line. I'm going to fit a line and just hope for the best because I don't have more data. Okay. Can you guys hear me in the back still? Am I OK? OK, let me know if you can't hear me. The battery just ran out on this thing. If you can't hear me, just raise your thumbs, wave your hands, something. Let me know. OK. All right. So this is the real world. So this is in the real life situation, there's some relationship between x and y. And what we get to see is this. Okay, so we don't get to see the real line. All we get to see are the points that got generated from that line. And because we only get to see these points here, if we draw the regression line through those 4 points, we're not going to get back the real regression line, right? We're going to get something maybe a little off, maybe a lot off, right? And our question now is, OK, we have some points. We can draw the line. But how good is our line? How good are our predictions? And that's the topic for today's lecture. So I'm going to show you a little demo, which I also showed at the end of Friday's lecture. So let's run this. I have here a bunch of functions that we use for linear regression. So here's a correlation. Here's slope, intercept, fit, plot residuals. All this we kind of wrote or kind of showed at the end of Friday's lecture. So here we have the functions. I want to run this function. I'm going to explain this to you. So what's happening here is that here is the real line with some point rated around. Okay. And we get to see the line. So here are 10 points. We only get to see the 10 points that the line created. Okay, so here's a real line. Here are the points that we get to see. So this is the data that we collect from the world. And when we try to do linear regression on that, we draw the line points. And we can see in this case that the line and the real line were pretty close. So what we chose as a regression line was actually really close to the real line. But if I go, let's say I change the slope to 3, or better when I make the slope here. Let's say I do that. Let's check it again. So here we can see, OK, pretty close, but a little bit off, right? Pretty close, but a little bit off. If I do it again, you're going to get, you can see the different lines that we get based on the real line. If I increase that sample from 10 points to 100 points, what would you expect? You expect that because we have more data, okay, so we get to see only these 100 points. You draw the regression line, and here is our estimation. As you draw more points, your line should get closer and closer to the real line. And what that means is as you take more samples of size, chances are that your line will be closer. Kevin?
Is it a real line? That means the line of the population of points, right?
Yeah, so what we're saying here is this green line is the real line or the real relationship between x and y. For example, let's say this is the number of students in the class, and this is how many shoes, and the y-axis is how many shoes we're wearing, right? So if you see 50 students, you probably see like 100. Let's make this 2, yeah. Make this 0. There we go. So if we see 50 students, we should only see 100 shoes, right? But if I actually want to count the shoes, maybe someone, for whatever reason, we counted wrong, right? So we get some variation in the points here. But so what we're saying is this green line here is a real relationship between x and y. There is some relationship that we're assuming to be like there. And what we're saying is based on our data, how well do we actually estimate the real relationship between x and y, the real association? That's what I mean real. I'm saying this is relation, like the actual relationship between x and y. Any other questions with this? OK, so our question now, so let me do one more. I'm just going to change this to 400. We have a bunch of points. And we only get to see these points. But these points look pretty close together, right? When we draw a line, we also expect to get a really close line. This is pretty good. But in the end, when we get to see these 4 points, or when we get one set of data, if we have one set of data in a regression, we only get one line, right? So the question for today is, the question we'll ask first is, how close is the line's slope to the actual slope, right? How close is our slope to the actual slope? When we take a sample of 100 points, we do the regression, find the slope of that regression line, how close is that slope to the actual real underlying slope? What I'd actually like to do, and this should sound familiar to us because we've been kind of working with this for a couple of weeks now. So when we have a population, we've seen this situation happen before when we're trying to estimate the parameter of a population, right? So we have a population, we have a sample, and we're trying to find, let's say, the mean weight, the mean baby weight, right? So we look at our sample, look at the mean baby weight of that sample, and we say, OK, from our sample, we can get one estimation of the population weight, right? So one sample gets one estimation, go back to our population, and we try to see, like, OK, how close is it to our actual population parameter? In this case, we have one sample, again, one sample, one regression line, so we get one slope. Now we want a confidence interval for the true slope. Okay, so how much you talk with your partner, how you would construct a confidence interval for the truth. My hint here is that you use the bootstrap somewhere in there. So think about how, just like how we created a confidence interval for the population mean and the population median, you would create a confidence interval for the true slope. Go ahead.
Oh, yeah, that's the that might be a little bit less dense because your bootstrap would replace that. So there might be some points that you pick twice, or some don't cheat at all.
All right, so no worries if you didn't get it now. That's how I'm going to explain it. So the basic idea is just like how we bootstrapped our sample before to get another estimation of the population mean, we can bootstrap the scatter plot. So we have some points x and y. We can just select at random from those points again with replacement. That gives us some variation that will change the scatter plot a little bit. And then we can take those points and find the slope of the regression line through that bootstrap plot. Okay, so we take our points, bootstrap the points, get another resample, and then we can get a new regression line. Because we're assuming our sample is close to our population, and we're assuming that our resamples look like our original sample, this is, roughly speaking, kind of like finding the slope through another sample taken from the population. So because of that, we can do that a bunch of times and get a bunch of different slopes. Then we can look at the histogram of all those generated slopes. So again, you want to make sure that the histogram of these slopes is roughly bell-shaped, just to make sure we're meeting our criteria for the bootstrap. We can get the middle 95% interval of those slopes. That gives us a range of values, a range of slopes that we think the population slope is in. Right? Let me show you how that works. This is an approximate 95% confidence interval. This is how we created a confidence interval, pretty similar to how we did it before. We just bootstrap the slope instead of bootstrapping the mean. Let's try it out. All right, so here we go. I have some data here. This is pretty familiar to you at this point. This is the baby data again. And what I'm going to do now is show you the relationship here between gestational days and the birth weight. So how many days the baby was in the womb and how much the baby weighed when it came out. This is in ounces, this is in days. So here we go. So here are the actual points. And here is our regression line through those points. Okay. And it looks like here, this is the residual plot. The residual plot here, it's we see a clump of points right here on the x-axis. But overall, the points are kind of like half above here and half below. Here, it seems like a pretty random pattern. There are some like kind of random points here. So these are kind of weird. But it looks like overall, the data look pretty good and good for a linear regression. So we're going to do a linear regression. Let's find the slope. So when I run that, we calculate the slope of that regression line. Slope mean. So thinking about the units of what we're working here, this slope means that on average, if, let's say, the baby is in the womb for 4 extra days, or let's say 10 extra days, we expect the baby to weigh about 4.6 more ounces. Right? So every 10 days, another 4.6 ounces. Every 100 days, another 46 ounces or so. So this is our slope, and that's our interpretation of our slope. And what we do now is a resample on the scatter plot. Okay, so here, example, we get one line. Here is another resample. We get a slightly different line. So you look, it's kind of hard to see, but you can kind of look. This one right here goes through 225, 100, 225, 100. It's a little bit below. Let's try another one. So here is another one. So as we resample the points, we're going to take our sample, resample, draw the regression line. We see here that we get different looking lines, a little bit different. Okay, slightly different looking lines. So we have 4 lines here. What we really want to do is do this a bunch of times. So I put that code in a for loop. Okay, and this is just showing you that when we resample, we want to make sure that the number of points as we did before. When we sample with replacement, some of those points are now duplicated. Right? So some of these dots have 2 points on them because we resampled with replacement. So we could have gotten the same point twice. That's what gives us the variation that we need in order to draw those regression lines. Okay. So I'm going to do this 5,000 times and let that chug along. And what we should get back is, if I run that, what we should get back is a 95% confidence interval for our slope. All right? So we see here this histogram. Talk over with your partner your interpretation of this histogram. What do you think this histogram means? Go ahead. All right, so what does this mean? This means that if I increase the gestational days by 1, I expect the baby weight to go up by between like 0.35 to 0.55 ounces, roughly. So every 1 day gives me about this much increase in birth weight. If I go up by 100 days, and this will go up by like 35 ounces to 55 ounces, something like that. That's how we interpret this right here. Confidence interval is these. And again, we can see that we get an estimation for the relationship between x and y. And we can say, OK, we are 95% confident that the real population slope lies within these two numbers here. OK, so I have here a bunch more bootstrap slopes. So let's take a look at, run that. I just put the code that we wrote above into a function, so I can just call that function a couple of times and show you some different things. Okay, so this right here should get us about the same thing. So I'm plotting here, again, the gestational days versus the baby weight, and we get about the same confidence interval here. Okay, now let's see. Take a look at the baby table. So what we have here is a bunch of different variables. We can kind of ask, OK, what's the relationship between each of these variables? We can bootstrap and get the slope and get some estimations for what we think the relationship between any two of these variables are. Right? What about maternal age and birth weight? Or maternal age and gestational days? Those two maybe don't seem to really have a real relationship between the two. And so what we should get is some indication that there is no relationship between those variables. Okay? So let's think about that while I take attendance. Do that. And go for it. In the meantime, are there any questions about what we did here? Now's a great time to ask some questions. Okay, so we have here the baby table. We're looking at the relationship between maternal age and gestational days. Let's take a look at those on a scatter plot. So what we see here, maternal age on the x-axis. Now notice how all points are on these lines here. That's because all of these ages are rounded to the nearest year, right? So if they're rounded to the nearest year, then you get kind of like strips of points here because we get one strip for each year that we recorded. We can see that the slope of this regression line is not 0, right? It's not completely flat, but it's pretty close to 0, right? It's like not exactly flat. So we can't say from this that there is no correlation at all between gestational days and maternal age, because there is some slope there. But it looks like it's not that much of a relationship. In fact, it seems to us like if we went back to the population and grabbed another sample, that slope would probably remain about the same, like at 0, right? So our question now is, we get a sample, we observe a slope, we're happy. But what if our actual scatter plot got a slope just by chance, right? So what if we just happen to get, a sample that has slightly 0 slope, or maybe like slightly above, like slightly positive slope, but there is a real relationship between the two variables? What if the real slope was actually like flat? Like there's no real relationship between the two. We just happen to observe a relationship because of random sampling. Okay, so I showed that. So when we're looking at that, what we're asking is whether or not there really is a slope between x and y, right? So if there's actually a real relationship between x and y, we should observe that, okay, when we take multiple samples, that we don't really get a 0 slope in our samples. On the other hand, if there is no relationship between x and y, what we should observe is that maybe sometimes we get a little bit positive slope, sometimes we get a little bit negative slope, but overall, it looks like across all our samples, there's like no relationship between x and y. Sometimes we get 0 in there. Okay, so if you want to test whether there really is a slope, then we can construct that as a hypothesis test. Well, our null hypothesis is the slope of our true line is 0. No correlation between x and y. Our alternative is that no, it's not 0, it's something else. Okay, and the way we can do that is pretty similar to what we've done before. We just construct that confidence interval for the true slope, and then ask if it contains 0. And that's pretty much all we need to do. So let's take a look. If the interval does contain 0, right? So if I bootstrap some samples and we get some slopes, some of them are positive, some of them are negative, and so that means that our confidence interval contains 0 in there. That means that it looks like there's no relationship between x and y, because it seems likely enough that we could have gotten a sample that has slope 0. Okay, so let's take a look. What we're going to do there is I just need to run this one cell, because I already wrote the code and put it into a function. Just call that and let it chug along. So what's happening here is that, again, we're resampling the points. So we're taking this scatter plot here, taking a bunch more points, putting a line through them, doing that a bunch of times. And what do we get? We get a confidence interval that goes from -0.3 to 0.001. -0.3 to 0.001. It looks like we barely meet our 5% cutoff. Right? So it looks like, OK, on just that interval alone, we will conclude that, OK, it looks like 0 is in our confidence interval. Right? So we can't reject the null. In reality, though, and you see that like this value here is so close to 0 at your 5% cutoff, you'd probably want to say, OK, I really shouldn't make a real like hard and fast conclusion here. I should probably go get more data and make my interval smaller. Right? So here we get something that's really close to 0. We think that there's no actual relationship, but maybe there is. Maybe if we collect more data, we actually get like that interval shrinks so it doesn't include 0 anymore. Maybe it doesn't. So it's really hard to make a judgment call when the data are really close to your cutoff like this. But if the interval is smaller or larger, we can make a better judgment call about that confidence interval. Okay. Any questions about that? Okay, so yeah, so what I'm trying to show here is that that bootstrap method of taking the slopes can let us answer a couple of questions about our data. Right? So we can go from one prediction line to multiple prediction lines. And then we can say, OK, I think that the true slope lies within this range. Instead of the true slope is probably like 0.34. We can instead say, OK, we think that the true slope lies within the range of 0.2 to 0.4. And that gives us more, let's just draw better conclusions, and seems to be more accurate, because our one sample could have been off from our population, but we can make an estimate for the population and say that the population parameter probably lies within this range. All right, so we can do the same thing for prediction. So I'm going to close attendance. Any objections? All right, closing. OK, so looks like how we bootstrap the slope. We can also bootstrap predictions and get a range of predictions for a given x value. Okay. So if our data came from a regression model, right? So if that model we had with the real line plus the points being off a little bit, but half the time above, half the time below, then our sample regression line should be close to that true line. Because as our sample size gets larger, our samples start looking like the population. Okay. So our regression line should be close to the true line. If we pick a value of x, draw the regression line, look at the value of y that matches that x value, we can make a prediction for a value of y. We've seen that before. We've done predictions based on that regression line already. But what we can do now is, again, use the bootstrap that scatter plot, get new regression line, get a new prediction, and now we can get a bunch of predictions. If we repeat that a bunch of times and get the middle 95% of those predictions, now we have a 95% confidence interval for our predictions. So not only can we say, OK, our slope probably lies within this range, we can also say, OK, my prediction probably lies within this range as well. Okay, so really cool. Let's try it out. So here, what we have is birth weight versus gestational days. I plot that regression line, put this yellow line here, because we're trying to say, OK, given that we're looking at gestational days of 300, what do I think that baby's birth weight is? It looks like here we think that based on our sample, our single sample, our birth is probably like 130. Right. But what we can do now, I'm going to show you that. It's about 130. So what I'm going to do now is so I'm going to resample and draw a new scatter plot, and then draw a new regression line, and then make a prediction. Okay, so what I have here is I drew a line through the sample, and took a prediction. So I'm not showing you here the points that I'm drawing, but instead I'm showing you just the line that I got from a resample. And here is my prediction. It looks like for this particular resample, I got a birth weight of about 127, almost 127, versus before we got 129. So I'm going to do this. Let's say I draw 10 lines, so 10 resamples. I get a bunch more predictions. I can do this again for 50. Get 50 lines. That looks like a Skittles bag. 100 lines. And now you get a bunch of lines, a bunch of predictions. You can taste the rainbow here, right? So here we say, OK, it looks like most of our predictions are between 131 and maybe like 127 to 131, right? So we can not only say that our original sample makes a prediction of about 130, we can say we think that even though we only have one prediction from our particular sample, based on the variability of that prediction, based on the variability of that sample, we're going to say the real population value probably lies within this range here. This range. So put that code into a function. Let's take a prediction, a real confidence interval for the x value at 300. So I'm doing here 5,000 repetitions. It's going to take a little while, so I'm going to run these two below too, so we can talk about it while it runs. So here we go. We see here that, indeed, we get a confidence interval of about 127 to 131. That's what we observe up here. Right? We look at the middle set of points here. 127 to 131. And the width of the confidence interval is 4. talk with your neighbor about what that width means. What does that width mean to have a width of 4? Go ahead. So what does it mean in terms of my original prediction problem? Given my data, gestational days, or given some birth weight, like what can I conclude? And what does that width tell me about my prediction? Go ahead.
The lines fan out. Regressional to regressional fan out. We expect set it to be roughly the same in each, but we expect lines to go through them. That's why it's better to get.
All right, so the width of this confidence interval here kind of represents the uncertainty that we have about our original estimation, right? So we had an original estimation of 129, and we made a confidence interval, and we said, okay, the actual population parameter of that prediction should probably lie within like 127 to 131. If our width was small, then we're more certain about our prediction, right? If our width is large, then we say, okay, maybe it's between 0 and 100, but I really don't know. It's hard to predict. Okay, so in a sense, we get here how good it is. And the reason why it's important is because you'll notice that if you take a look at the original scatter plot here. So as we resample, right, we're going to get lines that look a little bit different. But on average, our lines will kind of go through the center of our data, right? So our lines kind of go through the middle of this cloud here. So if you resample, we get a new line. The line probably goes to the middle of the cloud with a slightly different slope and a slightly different intercept. So we maybe get this line right here that goes kind of through the middle, but also goes below the line here, right? So we're asking the question, OK, based on 300, what do you think my birth weight is? We can ask the same different values of x, right? So we can say, OK, maybe we want to ask, what about 250 gestational days? What about 350 gestational days, right? And what we notice here is that based on our scatter plot, it's probably going to be hard to make a prediction about 350 gestational days, or maybe like 200 gestational days. It's probably hard because we don't really have data within. We don't really have data here. We don't really have data here. We have lots of data here, right? So watch. If I try to make a prediction so before we were at 300, we're trying to make a prediction at, say, 330, right? So 330 is like right here. We have less data here. What notice? We're going to notice that the width of our confidence interval increases, right? This is not something you can get just by taking one sample and making one prediction, right? We have here some indication of the uncertainty of our estimate, right? So as we get farther and farther away from our data, our confidence interval also gets wider to represent the fact that we're less certain about our prediction. So this width here is like 8.9. It's pretty wide. If I go back into the middle of our data, so let's go from 300 to, let's say, like 280, so right in the middle of the data here, our interval gets smaller. Interval gets smaller. And indeed, we get a width of about 1.89, about half the width that we had before. Okay, so the width here varies. And the reason why it varies is because, let's go back up, sample some points. Generally speaking, the line is going to go through the center of those points, right? The slope might change a little bit, and the intercept will change a little bit. But in general, the lines will go through the middle of these points, which means that if we're in the middle and we're trying to make a prediction here, the lines kind of all come to the same place. So our estimation, our confidence interval is pretty narrow. On the other hand, if we go far away from our data, let's say we go to like 200, our lines here, we get some lines that may go through like, may get a line that goes like this way, might get a line that goes down like this, right? Might get a line that looks kind of flattish, right? The lines, as we get farther away from the center, have more variation in their y values. And because of that, we get a wider confidence interval because we're less certain about our predictions. Okay, so pretty powerful technique. And what we noticed here to recap is, so y is correlated with x. So our predictions of y depend on the value of x. But the width of that interval also depends on x, as we saw. It depends on where our data fall. Okay? And typically speaking, our intervals are wider as we try to predict things that are farther away from the average x value because we have less data there. If we have less data there, we're less certain about our predictions. And indeed, we should choose a method that reflects that. We should choose a method that reflects that. And this method is one of the methods that reflects the fact that if we get farther away from our average x value, we're less certain about our predictions on the y value. All right, so just to recap everything, I was supposed to show one at a time. I'm disappointed. OK, so linear regression only gives us one estimate. So we get one sample, we get one line, we get one estimation. Right? We get one slope, one prediction for every x value. But if we bootstrap that sample, we can get a range of slopes, a range of predictions. If you want to bootstrap the intercept as well, you could do that. I'll leave it to you to think about what it means to get an estimation for the intercept of the regression line. But if we bootstrap, we can get multiple estimations for different parameters of our population. Okay? And so what that means is using the bootstrap, we can take a single sample and draw a confidence interval for both the slope and the prediction line. And what I've included here is an image from a popular plotting library called Seaborn. If you take Data 100, you'll learn about Seaborn and how to use it. But basically here, some plotting libraries, especially statistical ones, come with this sort of bootstrapping behavior built in. So what you see here is some points. This is like the tip of the bill versus the total bill at a restaurant. The regression line in dark blue, but you're kind of like this light blue cloud, light blue area here, light blue area here. What they did there built in is if you plot that, they'll automatically bootstrap that line and give you a 95% confidence interval. And indeed, you can see as we get farther away from the center of those points, we get more variation in our confidence interval. Cool. That's all I got for today. I'll see you tomorrow.
Yeah.